Welcome to the next lecture in the NeuronTalks series. It is my pleasure to host Michele Romani, all the way from Italy. Michele is a PhD student at the University of Trento, specializing in, among other things, brain-computer interfaces and their applications in gaming. And today, Michele will deliver a lecture on Neurogames. What does it take to control a game with your mind? And he will cover the components of a neurogame, the different types of BCIs applied to games, and how to use neuroimaging data. If you have any questions, please just ask them in the comments. And thank you once again for joining us, Michele, and the floor is yours.
Thank you for having me. It's a real pleasure to talk about the topic that I really like. And yes, the title of the topic introduces a very broad speech, a very broad lecture. So I hope this lecture will give the understanding of the big picture behind making a neurogame. So I will not go too specific into anything, but I will just touch all the points that I think are essential to understanding how do you make a neurogame and what are the difficulties. So I am actually a PhD student in the CIMI lab at University of Trento, which is Creative, Intelligent and Multisensory Interaction Laboratory. The title of my PhD is BCI for Gaming, so it's also sounds pretty broad probably. What I actually work on is the plug and play experience, so creating BCIs that can be used right away. So that's the real challenge, creating something that is pre-trained and generalized on basically any type of user. For this lecture, so I will show something that I worked on in the past few months. But before, I think we should also introduce what is a BCI, a brain-computer interface, for those who are not very expert of the topic. So it's a system for controlling a device, for example, a computer or a wheelchair or neuroprosthesis, and only using the human intention. So it does not depend on the brain normal output, which means the body, but just on the brain intention. Also, a BCI system has an architecture. So it's often called user BCI system because this architecture includes the user as part of the system. You will see probably many variants of this if you are into the field, but generally every BCI has a data processing unit, a feature extraction unit, a classification unit, and a command unit, which is basically the user interface. So the user interface, but the user interface is not necessarily a screen, right? It could be, as mentioned before, a wheelchair or a cursor, a controller that is physical. And through this interface, the user receives a feedback. So the whole loop is called neurofeedback loop, right? Starting from the user brain back to the feedback interface. There are also multiple types of BCI. They are usually grouped under these three macro categories. So active, reactive, and passive. And furthermore, active and reactive are grouped together as intent interaction. So active is the conscious generation of brain activity. That includes the motor imagery, so imagining the movement of a hand, an arm, a leg, and it's used for navigation and prosthetics. Then there is reactive, which is unconscious generation of a response, and it's a response to stimulation. So this is, for example, the steady state visual evoked potential or the P300 speller. So this type of BCI uses stimulation for creating a reaction in the user brain, and the user brain, knowing that there is a reaction, can focus on stimuli and decide which one to pick. And then we have the other big category, which is the passive for unintended interaction. So usually is the type of interaction that happens in the brain without the user consciously controlling it. And it's often used for support systems. So user state detection, emotion recognition, and event error-related potential, And this is also can be used to create a BCI. So the user to a certain degree knows that the brain is an input, but cannot exactly modulate it. So it's more like a system that helps the user. So for each of these, we can bring an example. So for example, okay. The active BCI, the main application, the main paradigm application is the motor imagery. As you can see, when you imagine one movement, for example, the right hand or the left hand, the brain has a different activation that can be used either if you have or you don't have your hands. So just imagining the movement is sufficient to activate certain areas of the brain that can be classified and then used for control. Then we have the event-related potential. So there are multiple potentials that depend on which type of stimulation is chosen. But generally, there is an event. And after the event onset, the event potential happens, right? So the event usually is called time zero. And after time zero, after a certain delay between 100 and 700 milliseconds, a potential happens. And that can also be used, classified and used as an input for example, a game. And then we have the passive BCI, for example, detecting mental states. Usually this is done either through regression or classification with a threshold, right? So we have some features that represent, that may represent the low attention or the high attention in this case, that are based on the power bands. So the theta and low beta power bands. And a combination of these measurements will give a value. And if the value is above the threshold, then it's classified as low attention. If it's below, it's classified as high attention. And this can be used for adaptive interfaces. So for example, an adaptive game, an adaptive task, an adaptive anything. So now we can jump on the gaming part. I am probably not sharing my video in this presentation, but that's fine. I will talk over the videos. So in this case, we have an example of neurorehabilitation. Let me see if it starts. It's always funny that I don't understand how Google Meets. Okay, I can start it probably. Can you confirm the video is moving?
Yeah, it is.
Okay, cool. So this is an application for neurorehabilitation. So the user has to imagine the movement, and the user is taken from a pool of subjects who suffer stroke. So they have difficulties in moving their real hands, but being put into a virtual reality environment, they can imagine to row and slowly regain control of their limbs. This can also be done in pair with electrical stimulation. In this case, it's only imagined movement, so there is no electrical stimulation of the limbs, but they report successful recovery. So neurorehabilitation is one of the hot topics of BCI, and games are a very good motivational tool for this type of therapy. Then moving next, of course, there is the whole point of accessibility. So creating games that can be used by people who do not have normal control of limbs. This video is taken from the Cybathlon, which is a yearly competition in creating this type of games and also in competing with other players using these games. So this is totally aimed to a population who is more fragile and affected. And of course, they want to play games like everybody else. So in this case, the technology comes in their help. And it's really life-changing, like to be able to use something that you would normally not be able to use all alone. So the Cybathlon is a very great initiative. I recommend you check it out because they really have very cool applications, and you can only participate if you have some impairment. So it's an event that is really dedicated to BCI games and competition. Then in this case, we have a passive BCI. It was an experiment on ADHD, which is a neurological disturb. So basically, in this experiment, they were designing a neurofeedback training for people who have difficulty in focusing, so attention caused by inattention, impulsivity, or hyperactivity. So by creating a virtual environment and a game, the user can receive a feedback on how they are holding the focus, and then they can basically they can learn how to control their attention through the game. So this is one of the application of passive BCI that is also getting popular. There are already some products for this, and also some studies. We have done something with the ADHD population, because it's becoming a very often diagnosed neurological disorder. So if games can be beneficial in studying this disorder, then it should be done. So yes, you can see the immersive virtual environment here. Then, as I mentioned, we also did something with ADHD. In our case, the student that I was supervising wanted to know if a gamified task makes it easier for the subjects with ADHD to use the BCI. So here you can see that basically the task was a combination of commands in a random sequence, and I was simulating the input to shoot the video, but that has to be done with the brain. And after this task, we were collecting some performance metrics to understand how fast they were, how many targets they got correctly at the first try, if the training was repeated, or it was possible to do it only once. So we got some interesting finds. For example, that all players reported to be much more motivated by playing the gamified task, but some also reported to feel distracted by the animation and the increased amount of elements, because the non-gamified version is the same task but without any background, without any dialogue. It's just the commands. And also the gamified had a better score when we had only 2 and 4 commands, but the non-gamified had a better performance in over the population with 8 commands. That exactly is coherent with the report of the user that said there were too many distractions in the scene. So that's also something that we do in our group. And okay, well, if we can go further here. Cool. There are also applications for simple entertainment. So you can just make a new game for the fun of it, the fun of making it, the fun of playing it. And there are also some commercial products like this one, for example. It's called NextMind. So this is a specialized EEG that works for visual ERPs, and it was commercialized a few years ago. So it's already possible to find on the market EEG devices who are easy to wear, easy to use, easy to develop with, right? So this video is very long, so I'm not going to show all of it. But the time that this device came out, many game developers and YouTubers made tutorials on how to make this type of games. I also made a few games just for entertainment and, of course, for studying how to make BCI and BCI games. So, for example, I have this game in which through ERPs, you can select one command and use it to trigger a shield and protect the base from the alien invasion. So this game, for example, does not need a specific device. So it's not a game tailored to a specific product, but it's made with Unity. So it's compatible with multiple platforms. So I show you the games and application, but of course, behind those, there is, first of all, data. And there are many neuroimaging techniques for creating a BCI. So we have 2 macro categories also here. One is the invasive technology, and the other one is the non-invasive. Among the invasive, we have the electrode arrays and electrocortigraphy. And the main advantage of invasive is that the quality of the data is really good, and you can have high spatial and temporal resolution, which means that you get you get to cover all the areas of the brain that you want, and you get a very fast response. Of course, the bad aspect is that you have to open your skull, or in the best case, you have to insert needles into your skull, which is also something not very feasible in the everyday life. So this is usually only for people who really need this type of therapy. Imagine, for example, Neuralink. That's this type of technology that only a surgery can implant in your brain. And then we have the non-invasive, which includes EEG, fMRI, FNIS, MEG, and PET. So some of these are very expensive and also not very portable. For example, PET and MEG. So those are devices that cost different, several hundreds of thousands of euros, and they are for clinical assessment. So they are in the hospitals. And then you have FNIS, fMRI, and EEG who are more portable. They have portable versions. And there are trade-offs. As you can see, for example, EEG has a very, very good temporal resolution and a very bad spatial resolution, while fMRI has a very good spatial resolution, but a very bad temporal resolution. So there is always a trade-off you have to choose for these technologies. And in particular, EEG became prominent in BCI because it's also cheap. So it's not just fast in responding, it's also very cheap. And for many applications, you don't really need to cover the entire brain. For example, as I said, it's not just cheap, but also fast, easy to set up, and it's great for real time. It has poor spatial resolution, which is not a terrible problem, but it's also sensitive to external noise, it's sensitive to movement artifacts. And if you're doing an experiment, like for science studies, you probably require gel or saline solution. So here I did a recording with this device, but I'm not sure you can see the. Can you see the video here?
Yes, it's something is
Okay.
moving. Okay.
Yes. So there was a signal. I applied some filtering because the signal was very, very noisy. And this was done with a very consumer EEG. So it's an EEG with just 4 electrodes, but it's the one I decided to use for showing you that it's actually possible to do some interesting machine learning also on this type of data. So normally, since the EEG signal is a non-stationary sinusoid, we have to clean away everything that is not interesting. So everything that is spurious information, starting from the power line artifacts. For example, in Europe, you have to filter away the 50 hertz frequency. In the USA is the 60 hertz. If you have a high sampling rate, you also have to filter the multiples of these, so 100 and 120. And then you can use a bandpass filter to select the frequency bands of interest. So you probably don't want to get from delta to gamma wave, but you want either a subset like alpha, theta, and beta, or alpha and theta, or theta and beta. So a bandpass filter can help you in achieving that, and also removing some slow drift artifacts. Okay. So here I have an example of real-time data acquisition with events. So in this case, I'm focusing on event-related potentials because that's what I did mostly in the last few months. So ERP's classification and games based on ERP. You can see in the bottom right a scene from Unity in which there is a target flashing. That's a training target. And you can see in the trigger channel some values coming. So these values corresponds to the 3 classes in the scene. So the training class is the one, then we have 2 on the right and 3 on the left. Why are they all coming when only one target is flashing? Because for the training, you need to know which one is the target and which one is the non-target. So in this case, 1 is target, 2 and 3 are non-targets. So after the training is done, all of these triggers are saved into the data, and it's possible to use it as labels for classification. Yeah, now it's a bit slow, but there is also an application mode later. Rock curve, so in this case, it was a very bad classification because the rock curve is around the random classification. So in application mode, you would see all targets flashing sequentially. And in this case, you don't know which is the target and which is not. You need to have a classifier already trained to tell you, hey, this is where the event happened. And if the recognition is correct, the right target is selected, and then you can associate that to a command in Unity. This is the data that I got from this recording. As you can see, there is quite some noise because when you save the data, you don't save the pre-processed and filtered data. You save the raw data normally, so that you can use it for other experiments or to try different type of processing. So you can see the placement of the electrodes were 2 on the central part of the head, and the other one were basically reference electrodes. I still access them for data information, but the information near the ear is a bit less informative for the ERPs. And I applied the common average referencing in this case. So to remove the power noise, as I mentioned before, I used the notch filter, and then I decided to filter with a bandpass between 1 and 30 hertz to remove the delta and gamma waves. So this is what remains after we have filtered. So now the signal looks a bit better, a bit more manageable. And for the second part of the processing of the data, we need to epoch the data. Epoching the data means getting this label, this trigger events saved in the data, and cutting the signal into segments. These segments can also overlap, so I can decide the length of the epoch to be 1 second. And since those were half second apart one from each other, it means that they're also overlapping. But that's fine, because what we want to find is the ERP wave. And the ERP wave will be only, like the right one will be only after one of these labels. So, and at a certain point in time. So if it's shift by half a second, we know that it's not the right class, the one that we are analyzing. So after epoching the data, we have T targets and NT targets, and those can be hot encoded into 0 and 1, which is important for classification. And after each of these events, there will be a ERP or not the ERP that we're looking for. So this is, for example, the ERP we're looking for. It's similar to a P300, meaning that it's a positive increase almost after 300 milliseconds. So why it's not a P300 is simply because the P300 requires some disparity. So it's for the oddball paradigm. So when you're looking for something that appears in a lower probability than the rest of the set, in this case, the probability of the target lighting up, flashing, is even, is the same after every second. And so it's a bit different ERP. And you can see that in the non-target epoch, this wave is not present. So now what we do is usually create a feature vector that can go into classifier. In standard machine learning, that means basically flattening all the channels into a single array. So you see that those are the 4 channels of the device, and the feature vector that results is this one. Okay, so this is for a single epoch, so a single sample of the dataset. Then what we do is that we split training dataset and test datasets with a 80-20 ratio. And then we try to validate the ability of the model to learn. We do it in this way. So we train the model on the training dataset, and then step by step, as the training proceeds, we do a little validation using our unseen data. And this tells us that after around 400 samples, we are already above 90%. I have to admit I did some data augmentation, because as you can imagine, when you have 3 classes and only one is flashing, there will be some disparity. So you will have a lower number of targets compared to non-targets. So I did some oversampling of the of the minority class, and that can lead to overfitting. So I also had to check, thanks to cross-validation, if there are biases or if the model is overfitting. So thankfully, the model is pretty good, meaning that when I have a target, I always predict target, and when I have a non-target, 97% of the times I predict non-target, and only 3% of the times I predict target. So the accuracy is around 98%. We can also see it here in the receiving predictive characteristic curve, the ROC curve, that the mean area is around 99%. So this was a good specification. And also it's a simple task with a sufficient amount of trials. But normally, if you also use shell, you would reach 100%. So classifying ERPs is an easy problem. The hard part is generalizing across multiple people. That becomes really hard. So at the moment, every time that you want to do a session with this type of BCI, you have to calibrate from zero the model for at least 60 trials, more or less 60 seconds, something like that. And then you can have a working classifier. New player comes, you have to repeat the process. So the real challenge is what we do after that, right? And that's what I'm working on for my PhD, and we will not go further into that. Now we discuss about the essential components of the NeuroGames. So we've seen that we have data processing, feature extraction, classification, exactly like in a BCI. So the NeuroGame is fundamentally a BCI in which the control interface is the game itself. And the game has other components necessary for the experience to be enjoyed. So you have a calibration and feedback components, you have the input, you have the lore, you have the game logic, and you have the in-game metrics, especially if your game is for research. So let's go through all of this. So the game input is an important part because it's up to the developer and designer to decide which is the right input. But as of now, replacing an entire Xbox controller with BCI is not really feasible. Like it's too slow to replace all these commands and have appreciable performance. So only a very small amount of players would be willing to do that, those who do not have other ways to play. And at that point, you probably want to combine maybe eye tracking and BCI if you have to control more than 5-6 commands for a game. But there are multiple combinations of input that can still make up for a good design. So first one is the classic single player pure BCI. So there is no input from any physical device. And this is probably what you want to do for somebody who does not have access to mouse and keyboard or joystick. Then you have single player hybrid BCI. So this is combining even classic type of input, but not necessarily, can also be combining EMG, or it could combine, for example, pedals. So I just reported the example of the joystick because that's the one I also did. So in this case, the BCI is only used to control certain aspects of the game and not all of them. For example, navigating the menu or moving the character around is done through the joystick. Then we have the multiplayer co-op BCI. In this case, you are dividing the commands of the player between two human players, right? So for example, one player is only shooting with the BCI and the other player is only moving the character, right? Or one player is powering one engine of the spaceship and the other player is powering the other engine. So there are multiple ways I've seen this implemented. This is also a very cool type of experiments for coordination between players. And that's totally a possibility. And then we have also this combination. So when one player is using a standard controller and the other player is using the BCI, which is also an interesting concept, for example, for tower control games. So one player is running around and the other one is monitoring from the control tower and helping out on the field. And of course, also in this case, there are multiple possibilities of what a player does and what the other do. And you can also imagine to have a CPU player in this case. So it does not need to be a human player, but it could be a CPU player moving around and you have the CPU. So there are multiple combinations, but those are generally the ones that are more interesting for the implementation of a neuro game. Then we have the game lore. So every game, even the arcade games, need a lore to immerse the player into of course, the role of the protagonist. For example, in one of the games they made, the lore was very simple. Mysterious aliens are attacking the space station. Only a hero with a great mental strength can recharge our shields, right? So at that point, you can start developing further the game lore. For example, are the aliens all the same? Are all going to the same speed or doing the same type of attack or going into the same direction? Are there any boss fights? And if so, how is this boss fight different from fighting a normal alien? Or does the protagonist have different powers? So for example, you saw the shield before. Are there any other BCI powers that can be activated every now and then? And what is the progression of the game, right? So how does the game progress further? This is always a complicated question that we will now go further later. For example, in the other game that you see in the screenshot, there is a combination of destroying the enemies, but also unlocking doors following certain combinations. So the progression increases either the number of enemies or the difficulty of unlocking the door or the time available for unlocking the door. The game logic is of course comes after the lore. In this video, you can see my girlfriend playing ping pong. So for the game logic, we mean the structure and the rules of the game, the levels as well. So the game logic should reflect the input choice, your BCI game or an BCI, and also the difficulty of the game. Like the game, now in this case, the difficulty does not increase because I was testing out how people react, and I didn't know exactly how to make the game in the beginning. So I was just checking out their reaction and see, okay, this is working, this is too fast, this is too slow. And there is also learning curve that you have to keep into account. So some players are naturally born skilled players, others are naturally born PCI players. You never know which kind of player comes to your game, so you probably have to keep a very low difficulty in the beginning, but then allow progression to take over. It's very difficult to balance a mind control game because of this also difficulty in training a BCI. For some people, it's straightforward. They just focus on the target and it works. For some other people, it's totally not easy. For example, if they also have ADHD or other neurological disorders, and maybe they don't even know because they're not diagnosed, it could be really hard to focus on a flashing target for 60 seconds. I also give some ideas. For example, the analysis of the player in-game performance. You can collect metrics of the performance of the player and try to adapt the difficulty based on how the player is doing. Or a more ambitious thing would be to compute a workload index. Since we have access to the brain input, we have access to the EEG or other type of neuroimaging signal. So we can try to adapt the game based on a workload index. That would be also something very cool to do. Anyways, the difficulty in the progression can and should be tied to the number of BCI commands available, or maybe the duration of the focus required to trigger a command, or maybe the combination of the sequence of commands. So there could be longer combinations or harder combinations or less time available, and the speed of the game can increase. So there are multiple ways that we can define this progression and make it actually enjoyable. Then another important part is the calibration of the game. So in the case of my games, for example, the model is not pre-trained at the moment. So calibration is a necessary step and can only be achieved if a certain cross-validation is reached. So if the cross-validation does not reach at least 80% of accuracy, the game does not start. So also good calibration needs to have clear instruction so that the player knows what to do, especially if it's the first time that they are trying the game. Then probably a seamless integration with the game, for example, the rules, explain the rules or the tutorial during the calibration is also a good idea so that it does not become a burden to the calibration for the player. And also we need visual cues for the classified quality. What does it mean? I'm going to show you. So in this game, the one with the aliens, what I did was to merge the tutorial with the training. So the player sees one enemy coming and the shields gets activated even if they're not focusing correctly on the target. Like they need to focus on the target. They know what happens when they focus on the target. The shield activates. Maybe they also think they did it. But the important thing is that they see how it works. And then after the cross validation is completed, I decided to color, wait, I will just pause it in the end. I decided to color the command console of the space station in green if the cross validation was above 90%, in yellow if it was above 80%, meaning that the player knows it's not amazing, like yellow usually is a warning, or leave it red if it's not working, right? So with red, the player also knows that they have to repeat this calibration phase. Of course, this is a very simple gamification of the calibration, but that's what we should aim when we are making neurogames, like to make the experience immersive from the beginning to the end, and also as transparent and self-explained as possible. All right, let's go next. Also, feedback is important. What do I mean by feedback is that the user needs to know the state of the BCI system. For example, one very common thing is the quality of the signal. So if the signal is conducted well, and if the signal is not being interrupted, for example, if the device is connected through Bluetooth, it can happen that there is packet loss. So you have to provide some visual components for this. So the system can also react accordingly. Like the user should know what's going on, but also the system should know what's going on. An example of this is, for example, disabling BCI commands when the signal is not of good quality, meaning that the player is probably not giving correct input. And so we are preventing the player from making mistakes if they're moving around and creating motion artifacts. So in this case, this is an example of visual feedback. So I have a bar representing the electrodes of the device. It's green when the impedance is low. It's red when the impedance is high. I also have a visual cue for the classifier in this case. So the other game, I had the green, yellow, and red on the console. In this case, I just provided a summary of what can be. So red bad, yellow good, and pink is perfect. I also did another project. This one is about music. And so in this case, we had a musician playing, and the interface of this application is still made with Unity. So it's some kind of game in which the musician can decide how to change the soundscape of the application. But of course, musicians also want to play some solo moments in which they are headbanging and moving around. In that case, the system deactivates automatically the BCI command. So it's only accepting BCI commands when the musician is focusing on the console. And then, yes, the rest we connected to some mixed reality application. But that's an example, and it was my first time using the signal quality as a way to improve the experience, because before the testers were reporting that sometimes they were just playing music and the BCI was activating and doing stuff without their intention. So in this way, we managed to solve. It never happened that the signal of good quality was overlapped with a headbanging. So it was totally a good workaround and escamotage. And then I mentioned the in-game metrics. So there are some games who are most often common in BCI, which are the task accuracy, so the accuracy in the online mode or real-time mode, call it as you want. The information transfer rate that represents how fast the BCI is, how fast we can send a bit of information for a trial, a second, a minute, or the completion time of a task. And by task, I also mean level. I mean any frame of the game that can be identified by a beginning and an end. Or, for example, the error rate, so how many times the user makes a mistake. This can be the complementary of the accuracy, so the error in the accuracy, or it can also be an error rate related to understanding the instructions, the rules of the game. Some examples, for example, in this pilot study from the Green Shield game with the aliens, I was collecting the task accuracy, so there were 30 enemies for each trial. And so players, of course, had different accuracies. Some players got 100% accuracy the first time, and others got a way low accuracy, like around 50%, but then trying again for another session the game, they definitely improved. So also proving that learning how to use a BCI is part of creating neurogames. So nobody, not nobody, but many people don't get it the first time, right? Just a few people are able to get the comments, especially if they tried some BCI already. Another example here is in my brain pong game, I was collecting how many balls were hit and how many were missed every 4 exchanges. Why that? Because I wanted to, like the game is endless until you score a point. So I wanted to have very precise measures. So every 2 times the balls goes from one player to the other, I wanted to measure how fast was the BCI. Of course, in this case, the speed of the BCI is also related to the speed of the ball. Like there is at that time when the other player is getting the ball, that the BCI is, you can give input to the BCI, but it's not hitting the ball. So in this case, the speed was locked to 9, I think. The information speed was locked to 9 bit per minute, which is not very fast, but it's very good for this game, right? So the speed only decreases if you miss the ball, because then it becomes longer to complete the 4 set of exchanges. So in conclusion, I've been talking quite a while, but what is the take? That making neurogames is not very easy, and is still the domain of researchers and developers that have a strong passion for computational neuroscience and game development. So it's a set of very specific skills that not everybody can have. Probably if you're doing a bachelor or a master, you have to choose what to focus on, and you cannot do everything. But the lucky thing is that the BCI technology is getting more accessible, it's getting more standardized and more flexible. So you probably don't need to have 2 or 3 specialization to make a neuro game. You can just have one specialization, for example, in data science, in neuroscience, in electrical engineering or biomedical engineering, and the technology to build BCI is easier now than it was 10 years ago to use. It's easier to integrate. Also, making games has become easier thanks to Unity and Unreal Engine and Godot. So there are now game engines who are very powerful, and the companies who make EEG technologies or BCI technologies in general are more interested in creating integration for this type of tools. So this is definitely the right time to start making neuro games. Those are my references. I will share the presentation later if anybody wants to check. And thank you so much for your attention. And if you have any questions, I'm available.
Yes, I do have questions. Yeah, you said that like right now BCI is too slow to replace like the controller. And what do you think is why do you think it's that? Is it because of the poor signal? Like, would it work with, for example, Neuralink?
Mhm. Also, Neuralink would be slow because you have to map every action to different things in the brain. So let's do an example. Maybe you want to use a combination of ERPs and motor imagery. Okay.
Mm.
So for motor imagery, if you're using a low amount of electrodes, the best you can do is probably 4 classes. 1, 2 arms and 2 legs. You can classify, imagine those. You cannot classify moving each finger. That's something that Neuralink can do, actually, classifying the finger movement. But also Neuralink is positioned in a very specific area of the brain, does not cover the entire brain. So again, there is some trade-off. So you can combine motor imagery and ERP and get maybe, what, 8 classes at a decent speed. But an Xbox controller has up, down, left and right, A, B, X, Y, RT, LB, RB, and what are the others? I don't remember, but like there are at least 16 commands on one of these joysticks, right?
Mm-hmm.
So probably you don't need all of these commands to play an average game, but if you're playing Call of Duty, that's another story.
Right. Yeah, so it kind of depends on the game because I think that like the first user of Neuralink, I think that he spent the first night like after like getting the implant playing Civilization 6. So yeah, maybe for that kind of game it is possible.
What they did
Like,
in Neuralink was mapping a mouse cursor, so the direction of the mouse to motor imagery. And
yes,
so he was imagining left, right, up, and down, and then probably had one command for clicking. And for civilization, that's perfect. You only need
yeah,
those commands.
yeah, that's right. Another question. What do you think the future of neurotech gaming will look like? Like how it will proceed?
So I think that the interesting applications for neurogaming are accessibility, of course. So making games more accessible for people who do not have full control of their limbs, and research. So researching on games, using games for researching certain things, right? This is the near future. So something that people already want to do now, and so they have interest in building games or using game for this type of experiments or for improving their life. The near future, which is near I mean it's not very far, it's just that we have to create the interest, right? The market interest probably are hybrid games, so games in which the brain is part of the input, but maybe not does not control the entire game. Maybe it's just for power-ups, or maybe it's for a certain class of players and not another one. So that's one thing in which I see a very good fit, especially if you're thinking about VR games. So games that have a lot of 3D spatial environment, and having the brain to get additional input to, for example, focus on targets or reach a certain area, it's way more interesting than on a flat screen, right? When you don't have a mouse. And the other thing that I think is going to be very interesting are adaptive games. So understanding what the player is feeling while playing the game, or what kind of player is that, if it's an aggressive player or a shy player or a relaxed player, and then adapting the game, so tailoring the experience of the game for this player. And there are multiple games who are focused on anxiety, depression, or even schizophrenia. Like there is Hellblade: Senua's Sacrifice, that is a game about schizophrenia. I see a very good fit for this type of games, even horror or maybe thriller, to know how the player is feeling, so that they can adapt the experience to the player.
Right. Yeah, and speaking of accessibility, what do you think about BCI slash paradigm, like illiteracy, illiteracy? Like, should game developers adapt, like, for example, many paradigms in case somebody like does not respond to a specific paradigm?
I think that my dream controller using a BCI has a little bit of everything. So has a bit of ERPs, of course, because they are very easy to use and very useful, but they cannot do everything. A little bit of motor imagery, a little bit of passive And for example, the error-related potential, that's a passive application that tells you, like, you have it's basically an ERP that happens when something does not go as expected. So when there is an error, for example, so knowing that the player knows that this interaction was not what they intended is a very powerful tool for making games, and has not been very much explored because it's a bit harder to develop, but it's totally there. It's totally possible to do. But also combining other type of sensors that are easily available. For example, eye tracking, either through cameras or other type of trackers, and muscular activity, EMG from the wrist, that should totally be part of these accessible controllers, so that even people who do not, so people who are impaired, of course, can benefit, but also people who are not necessarily impaired can use the technology very quickly, right? So, because that's the point. It's hard to replace mouse and keyboard or the joystick. Those are the fastest input method that we have since the 70s or something like that. So it's almost impossible to replace them. So we have to provide added value to convince people to use other type of inputs.
Okay, thank you. And we do have one question for our Portuguese fan. So you mentioned calibration process. What exactly does it mean? Your initial model is validated on a player data, and if the result is good enough, then they are able to play, or maybe have you tried to use calibration data to create ML model that would map user data to your initial model?
So by calibration, it really depends on the task, right? So I show previously, let me go back to the slide, this one. I showed previously this type of calibration. This one is through stimulation. So there is a stimulation that happens, and if the player focuses on it, of course, the ERPs are getting generated after the onset of the event. So this is one type of calibration, but it could also be instruction of imagine to open and close your hand continuously. That's also a type of calibration. And what I mean is that in this case, the model is empty. So I'm not, my model is not pre-trained. I'm not using the weights from another model. And generally speaking, when you calibrate on one person and save the weights and reuse the weights on a new person, just like that. So if I now take the data from this model that you see in the video, I save the weights and I load it into another player classifier, it will probably not be as good as it was for me. That's because every brain is different, every reaction is different, but also if I'm in a certain psychophysical condition, for example, I'm tired or I'm very excited because I just got 1 liter of coffee, that's going to create some difference. And you have to imagine that back when image classification was at the beginning, most of the models could not learn on cats and apply on dogs, right? And even if you were rotating the cat in multiple directions for these models, that was not a cat because they were trained on front-facing standing cats, right? So that was the first experiments in deep learning. And then they decided, okay, we see that the model needs different type of information from different sources. So they started rotating the cat. They started cutting the cats in for squares and moving it around. They started applying color filters. We have to do the same thing for EEG, just for EEG. Well, probably also for other signals, but each signal is different. So we need to do the same thing, like collect data from different people in different conditions. So when they're tired, when they're not tired, when they drank coffee, when they didn't drink coffee, when they make mistakes, when they don't make mistakes, right? And you can see it's quite a challenging thing to do because there are so many possibilities, and collecting this data is not like taking a picture and uploading it on the internet. You have to wear a headset, you have to prepare a protocol, you have to record the person, you have to mark every event and everything the person does if it's unexpected. So we will get there eventually. We will get there, but it will take some time.
Okay, I think that we don't have any questions left.
Cool.
So thank you for being here today, and thank you for the interesting lecture. And yeah, I hope that you visit us again in the future.
Thank you so much for having me. And yes, I'm always happy to talk about BCI, neurogames, video games. And so anytime, maybe I can take something more advanced for the next lecture.
Okay, thank you very much, and